Hello, this is Jim Corkins, and we're continuing on with 5.0 rotation lecture. And now, after completing statics, we're into dynamics. Now, statics and dynamics are pretty much the same thing, except with dynamics, there will be an alpha. With statics, omega could be constant velocity or zero. In either case, alpha was zero. But now with dynamics, alpha will not be zero. So you will have to consider the moment of inertia when you're completing these problems. Okay. So just like with statics, we're going to have to sum up the torques and set it equal to I times alpha. And that's how we're going to go ahead and approach and solve the problem. So we're going to be applying Newton's second law of rotation here. And basically what that's saying is when an object is spinning, you could call the center of that spinning wheel as basically being motionless, while all the other objects around it are moving relative to that center. Okay. So, for example, here we got a kid we got a person who's giving this wheel a spin. These three other children are spinning, but when they move to the center of the mass, they're not going to be really spinning anymore. They're not going to have any torques operating on them at the center of the actual disc. Okay. Now, again, just like like I mentioned before, what we're going to be doing is we're going to be identifying the torques, which we're going to be identifying the distances of the force to the pivot point. We're going to also identify if the torque is positive or negative, meaning clockwise is positive, clockwise is negative, and counterclockwise is positive. So we're going to be drawing a free body diagram from that, but also we're going to be identifying those torques and their signs. Okay. And from there, we're going to then solve whatever the problem is asking to solve. Okay. But it's important to just really quickly review moments of inertia. So if you have a moment, go back to 5.2 and review those moments of inertia. Many of the problems that we're going to be dealing with in dynamics are going to be working with disks or cylinders spinning or masses on the end of a string. So again, what we'll have to do is sum the torques, and if there's multiple objects spinning on one object, we're going to have to probably also sum the moments of inertia and then multiply that by alpha. Okay, so again, familiarize yourself again with the moments of inertia. All right. But let's look at how moment of inertia is related to angular acceleration. So suppose you're given this problem, and I think this is one of similar to a quiz question. You have two disks that are the exact same size, but one has twice the mass of the other. Which object has a larger moment of inertia? So both are given the same applied torque. So which object has a larger moment of inertia? And as a consequence, which one will have a larger angular acceleration? So take a moment, think about the problem, and then pause the video and try to answer it. Okay, please pause now. Okay, we're back. So to figure out which one has a larger moment of inertia, we're just going to note those moments of inertia right here. So since this is a spinning disk, its moment of inertia is 1/2 m r squared. Since both objects have the same radius, this object has 1 m, its moment of inertia will be 1/2 m r squared. Okay. But this other object over here has 2 masses on it, so it's got twice the mass, so its moment of inertia is 1/2 2mr squared, which is going to work out to be mr squared. So which one of these two is larger, 1/2 mr squared or 1 mr squared? So obviously this object on the right has a larger moment of inertia. Okay, well, comparing those two together, now we could actually talk about torque. So torque is equal to I alpha, apply Newton's second law to torque and rotation, and you get this. Now if we divide both sides by moment of inertia, we have a relationship of moment of inertia and torque to alpha. Since both objects have the same applied torque, that's not going to be something that we really need to consider. So since both torques are the same, let's take this torque right here. This torque is the same torque, and that's over this moment of inertia, which is going to be 1/2 mr squared, and that is going to be what alpha is equal to. This 2 is going to go up top, so that 2 is going to be, so this is now going to be 2 times the torque over mr squared. On the right hand side, this moment of inertia is mr squared, and that's equal to alpha, right? So this is effectively, this guy's acceleration is going to be 1 times torque over mr squared, while this other one is going to be 2 times torque over mr squared. In other words, we could say this as the one has a larger torque, a larger moment of inertia, it's going to result in a lower angular acceleration. It's kind of like saying having a larger mass, you're going to have a lower acceleration, right? If you have a bus and a sports car, they're in a race, they both have the same engine. The sports car is going to win because it has a lower mass, while the bus has a larger mass, which is going to result with a lower acceleration. So basically, to answer this question, this object right here has a larger moment of inertia, but a lower angular acceleration. This object will have a lower moment of inertia and a larger angular acceleration. And one way we could take a look at that real quickly with concepts is just by taking a look at this relationship. Okay? Let's try another problem. Okay? Now you have 2 objects that are different sizes, but one has a larger, one is twice as large as the other one. So let's say this one has a radius of 2r, while this has a radius of r. But they have the same mass. Again, they have the same applied torque. So, and again, you're trying to figure out which one has a larger moment of inertia, and as such, which one will then have a larger angular acceleration. So go ahead and think about the problem, pause the video, come up with your answer, and then unpause the video and come back and we'll talk about it. Okay, here we go. So this object has, it's a disk, so it's 1/2 mr squared, and this other object over here is going to be 1/2, and again they have the same mass, but this is 2r that is being squared. So this moment of inertia is going to work out to be, and I could just use the right hand side here, this is going to be 1/2 m4r squared, which is going to result with 2mr squared as its moment of inertia. So this is going to have a higher moment of inertia, and again from earlier, the one with the higher moment of inertia right here, one with a higher moment of inertia is going to have a lower angular acceleration. That's what we predict with concepts. Well, let's work it out. torque divided by moment of inertia over here is going to be 1/2 mr squared. And so this is the alpha for this guy. So that's again going to work out to be 2 times tau over mr squared. So this alpha is going to be 2 tau over mr squared. This alpha is going to be tau over 2mr squared. So this is going to work out to be 1/2 tau mr squared. So while it's got 4 times the moment of inertia of this other object, it's only got this other object here is going to have 4 times the angular acceleration of the larger object. Okay, so that's how torque and moment of inertia interplay to affect alpha. Okay, and that's the basics of dynamics. Let's move on to some more complex problems. Okay, so this is a much more complex problem. It's a great problem because it's going to make us practice the procedures for summing up torques, summing up moments of inertia, and seeing how those two affect alpha. Okay, and in this problem, you're given forces of 1 Newton here, 1 Newton here, 2 kilograms here, 2 kilograms, and they actually give you the distance in between both objects. And in all of these objects, they're spinning about the center of mass. So they're all going to be spinning counterclockwise, which is going to result with a positive torques and probably a positive alpha. Okay, but let's do A together. Okay, let me show you to do A together, and then let's see how you do on your own. So with A, again, we're going to sum the torques and set it equal to, we're also probably going to have to sum the moments of inertia and multiply it by alpha. Okay, so this is basically a ball on a string. Okay, so this is the angle. This is going to result with a positive torque. This is a positive torque, and they give you the force down. The force is 1 Newton, and this is a 2 kilogram mass. So when we need to do this problem right here, what we're going to do is we're going to go look up the moment of inertia for a ball on a string, which is mr squared. So in all of these cases, we're going to be using a moment of inertia, which is mr squared. And this r right here is going to be 1 meter. Okay, so let's do the torque on this first object right here. So that's going to be, torque is r times f. So distance r is going to be 1 meter. And it's a positive torque. And it's 1 Newton force. 1 Newton force. And it's at an angle of 90 degrees. So that's just going to be the sine of 90 degrees is going to be 1. So this is the torque for this left ball. We're going to add that torque. Again, we're just summing our torques right now. We're going to add that to this other torque over here, which is also a positive torque. It's 1 meter. It's also 1 newtons, and it's at the sine of 90 degrees. Okay. Now comes the moment of inertia. This ball over here has a moment of inertia of mr squared, so that's 2 kilograms times 1 meter that we're going to square. We're going to add that to the other ball, which is 2 kilograms times 1 meter that we're going to square, and set that equal to alpha, and multiply that by alpha. Okay, so we sum the torques, and then we're summing the moments of inertia, and set that equal to alpha. Moments of inertia will always add up, they never subtract. Okay. So this torque here is going to result with 2 Newton meters. This moments of inertia is going to result with 4 kilogram meters squared times alpha. And so dividing both sides by 4, we're going to get, so it looks like we're going to get 2 Newton meters divided by 4 kilogram meters squared. So that's going to be essentially 2 divided by 4. So this is going to be 1/2 a radian per second squared. And that's going to be our alpha for A. So go ahead and practice. I want you to practice and do B, C, D, and E for yourself, and try to repeat the procedure that I just did. Okay, so attempt all those and then unpause the video. So please pause now. All right, and we're back. Let's check out what part B is. Okay, so we're going to sum part B over here. We're going to sum the torques for part B. So when we sum the torques for part B, again, it's going to be a positive torque. And this left guy right here is 1 meter away. And it's 2 newtons of force this time. Okay, now we're going to sum the torques on the other side. So that's also 1 meter away and a positive torque. And it's also 2 newtons of force. Now let's sum the moments of inertia. It's going to be 2 kilograms times 1 meter squared plus 2 kilograms times 1 meter squared times alpha. Okay. So summing all of this together, this is going to be positive 4 Newton meters. And that's going to be equal to this side over here, the moments of inertia. It looks like it's going to be 2 plus 2, so that's going to be 4 kilogram meters squared times alpha. So this is going to be 4 divided by 4, which is going to be positive. So this is going to be, the positive is implied, so it's going to be 1 radian per second squared. And that's going to be the alpha for B. So right now it looks like B is greater than A. So it's going to be one of these two answers right here. All right, let's try C. So over here is C. And C, we're going to sum our torques. This is going to be a positive torque, and it's 1 meter away. And that's, maybe I could zoom in. It's 1 meter away. And that's the 1 Newton force is 1 meter away from the spinning, the pivot. And the other pivot is a positive torque, and this force is 1 Newton as well. Now we're going to sum our moments of inertia. It's going to be 4 kilograms times 1 meter squared plus 4 kilograms times 1 meter squared. And that's equal to, and that's multiplied by alpha. So right here, we're going to add these two up. So that's going to be 2 Newton meters on the left-hand side. On the right-hand side, that's going to be 8 kilogram meters squared times alpha. And then divide 8 by both sides, and that's going to give us 1/4 a radian per second squared. And that is the alpha of part C. Okay. Let's do part D. So part D, let's use kind of orange. Is that orange? That looks orange. So part D is going to be orange. So we're going to sum our torques for part D. And that's going to be, now it's 2 meters away. It's going to be a positive torque spinning it clockwise. So positive torque 2 meters away, and that's 1 Newton of force. This other force is also a positive torque, and that's 2 meters away, and that's going to be 1 Newton of force. Okay. Give myself some room. Now let's sum our moments of inertia. The moment of inertia of this is going to be 2 kilograms times 2 meters that we're going to square. 2 kilograms times 2 meters that we're going to square. We're going to be careful. This is not 2 meters squared. It's 2 meters that we're squaring. Okay. Plus the other ball is 2 kilograms times 2 meters that we're going to square. And then we're going to multiply that by that alpha. So over here on the left-hand side, that's going to be a positive 4 Newton meters of torque. This is going to be 2 kilograms times 2 squared. So this is going to be 8 kilogram meter squared plus 8 kilogram meter squared. So overall, this right-hand side is going to be 16 kilogram meters squared of moment of inertia times alpha. So this is going to be 4 divided by 16. So that's going to be 1/4 radian per second squared. And that is the alpha for D. So it looks like D and C have the same alpha. Let's do E together. So E is a little bit more complicated. It's the same thing as it's very similar to D, but we have this sine of 30 degrees. So again, these forces, even though they're diagonal, are going to be spinning it counterclockwise. So that would be a positive torque. They're also, this force is 2 meters away from the pivot point, and it's 2 newtons, but it's at a sine of 30 degrees. And if you remember, sine of 30 degrees is a half. On the right-hand side, this is positive 2 meters. This force is 2 newtons. Sine of 30 degrees, which is a half. Okay. And again, just like D, this is going to be 2 kilograms times 2 meters squared plus 2 kilograms times 2 meters squared. So that's going to result in 2 kilograms times 2 meters squared plus 2 kilograms times 2 meters squared. And that's going to be times alpha. So again, that's going to be 8 plus 8, which is going to be 16 kilogram meters squared of moment of inertia times alpha. This side over here is going to be 2 times 2 divided by 2. So that's going to be just 2 plus 2. So this is going to be 4. Make that look like a 6 here. So this is going to be 4 Newton meters of torque. So this side is going to result in 1/4 a radian per second squared, and that's its alpha. So what this looks like is it looks like B is the largest, A is the second largest, and then it looks like C, D, and E are all equal. So B is greater than A, which is greater than C, D, and E. So it looks like this is the correct answer right here. What I like about this problem is it makes you have to do all the procedural steps, summing the torques, summing the moments of inertia, and then multiplying that by alpha and solving for alpha. Okay? So this is a really great problem. All right, so here we have another problem. It looks like there's a satellite here, and it's got rockets attached to it at different points, and each of those forces are indicated right here, 30 newtons pointing up and to the left, and that rocket is attached here, and it's 5 centimeters away from the center of this disk. You have another rocket which looks like it's 10 centimeters away from this central disk, and is pointing to the right. You have another rocket pointed straight out, which is 20 newtons, and it also looks like it's attached at 10 centimeters out. And here we have another rocket pointed straight down, which is 20 newtons, and it's 5 centimeters away from the center of the disk. And they're saying that each of those rockets has a mass of 240 kilograms, and the disk itself, which is 3,400 kilograms, and the radius, I think there's something wrong with this problem. It should say the radius of this is 5 centimeters out, so that's going to be a radius of 10 centimeters. So 0.10 meters. It's a really small satellite. Okay. So let's go ahead, and I want you to go ahead and try what you just did, given what you just learned from the last problem. Try summing up all those torques, sum up the moments of inertia not only for the disk, but each one of these satellites that are 240 kilograms attached here. And those will act just like a mass on a string. And then figure out the directions of the torques and figure out the angular acceleration. So pause the video now. Okay, we're back. So what we're going to do is we're going to sum up our torques. Okay, and I'm going to start with this torque right here. This torque is kind of, this thing is attached right here. So it's at a perfect 90 degrees to the lever arm. It's 5 centimeters away. And if this were allowed to spin, it would spin it counterclockwise. So that'll be a positive torque. It's 5 centimeters away, so 0.05 meters. And it's a force of 20 newtons. And it's working at sine of 90 degrees, which is just 1. So we just did this rocket right here. Okay. Let's do this 30 Newton rocket. Okay. This 30 Newton rocket, I'm going to use red for that. So this is going to be, this is the red rocket right here. So this rocket is also going to spin it counterclockwise, which is going to be a positive torque. It's also located 5 centimeters away, and it's 30 newtons of force, and it's at 45 degrees, so that's going to be the sine of 45 degrees. Okay, which, let's just do that real quick while we're here. Figure out what 45 degrees is. Take the sine of that. 0.707. 0.707. All right. Let's do another rocket. Let's try purple. Let's call this the purple rocket. This rocket looks like it's going to be spinning it clockwise, so that's going to be a negative torque, it's located 10 centimeters or 10.10 meters away, or 10 centimeters away. It's 30 newtons of force, and this looks like it's at a 90 degrees. So that's going to be the sine of 90 degrees. So it's a 90-degree lever arm. So that's just one. And that's that torque. This last one right here, which is the easiest one, this rocket is located 10 centimeters out. It's not going to contribute to the torque at all. It's not going to make it spin at all. But we're going to go through the motions. So it's 10 centimeters out, or 0.10 meters. It's 20 newtons. But the angle here is sine of 0 degrees, which is just 0. So this whole thing is 0. Green is all just 0. Okay? So that's the sum of the torques. Okay? We're going to set that equal to this. We're going to set all of those, and now we're going to sum up the moments of inertia. But I want to do those separately. Okay? And maybe what I'm going to do is I'm going to simplify this left-hand side. But what we're going to do is we're going to sum up the moments of inertia over here. I'm going to show you what we're going to do. You have the disk itself, which is 1/2, and the mass of the disk is 3,400 kilograms. And it's got a radius of 0.10 meters that we're going to square. Okay. We're going to add that to the black rocket, which is a ball on a string, pretty much. And that was 240 kilograms. And it was 0.05 meters out. So 240 kilograms, and it was 0.05 meters out. We're going to square that. The other rocket, which I think was our red rocket, is also 240 kilograms and 0.05 meters out. The purple one is 240 kilograms, and it's located 0.10 meters out. Okay? And again, you sum up all the moments of inertia. So this is going to be 240 kilograms, and this is 0.10 meters out that we'll square. Finally, running into another slide from later on, is going to be the green guy. So even though the green satellite is not contributing to the torque, it still contributes to the moment of inertia. So that green guy is going to be 240 kilograms, and it was also located at 10 centimeters out. So this is plus 240 kilograms, and this is 0.10 meters squared out. So now we've summed up all of our rockets, 1, 2, 3, 4 rockets, and the disk. We're going to set that, and we're going to multiply all of those moments of inertia times alpha. Okay. because I'm going to zoom out, and I'm going to actually, let's look at the torques first. So this is 20 newtons. So this is going to be 20 newtons. Whoops. Let's try this again. So this first torque is 0.05 meters times 20 newtons. And that's going to be equal to 1. Okay? So that's just 1 Newton meter of torque. Okay, and it's positive. All right, let's do the red one. The red one is going to be 0.05 meters out. 20, whoops, that was supposed to be times 30. 0.05 times 30. So that's going to be 1.5 Newton meters of torque. And that's going to be positive 0.5 Newton meters of torque. Let's try the purple guy. The purple guy is negative, and that's a negative, well, this is positive, this is negative, so this is going to be negative 1.5 Newton meters of torque. Right? 0.10 times 30 is 1.5. That's a negative. The green guy is going to be 0 Newton meters of torque. Okay. All right. Moving right along. Let's look at our moments of inertia. This moment of inertia right here is going to be 0.1 squared times 3,400 times 0.5 equals, so 17. So that the disk has a moment of inertia of 17 kilogram meters squared. Okay, let's talk about the black. Let's figure out the moment of inertia of the black satellite. All right, so that's 0.05 that we're going to have to square times 240 kilograms. So that's 0.6 kilogram meters squared. 0.6 kilogram meters squared, which means the red one is also going to be 0.6 kilogram meters squared of moment of inertia there too. Now comes the purple and green, which are going to be the same ones. So that'll be pretty easy. So this is 0.1 that we're going to square times 240 equals, so 2.4. So the purple guy is going to be 2.4 kilograms meters squared of torque. The green one is also 2.4 kilogram meters squared of torque, of moment of inertia. And this is the alpha that we're trying to find. Okay. Okay, now is the time to start adding up our torques. So you got 1 plus 1.5, that's 2.5, minus 1.5, we're back to 1, plus 0. So the left-hand side is pretty easy. That's just 1 Newton meter of torque. After all that, just works out to be 1 Newton meter. Okay, let's add up this. This is 0.6 plus 2.4, so that's going to be 3, plus 0.6 plus 2.4, that's also going to be 3. So 3 plus 3 is 6, plus 17 is going to be 23 kilogram meters squared of moment of inertia times alpha. So this alpha is going to be 1 over 23 radians per second squared, and that is alpha. Okay? So when we figured out all of that, that's going to all work out to be 1 over 23 radians per second squared, and that's what alpha is. Okay? Boy, that's a lot of summations. So these last two problems that we just did are really good problems in practicing the steps of summing torques and moments of inertia. Let's take a look at this last problem. And I'm not going to do this problem, but I am going to talk about it. So you've got an airplane, and it's given a torque of 60 Newton meters. It's got basically a length. It would be kind of like a stick spinning about its center. So we'll need to know what the moment of inertia for a stick spinning about its center. So let's go up here. A stick spinning about its center has a moment of inertia of 1/12 ml squared. So let's write that down. Oops. This moment of inertia is, for this stick, is going to be 1/12 m times the length of it squared. It's not r squared, it's the length of it squared. So it's got a mass of 40 kilograms. It's 2 meters long. Okay. And it's asking how long does it take for the propeller to reach 200 rotations per minute. Well, let's just sum the torques real quick and set it equal to the moment of inertia times alpha. Let's figure out the acceleration. Okay. So the torque they give it is 60 Newton meters, and we're just going to assume it's spinning counterclockwise as indicated by this arrow. And that's going to be equal to 1 over 12, the mass, which is 40 kilograms, times the length, which is 2 meters that we're going to square, times alpha. So this is going to be 60 Newton meters of torque. This is 2 squared, so that's going to be 4. So 4 times 40, so that's 160 divided by 12 equals 13.33. I'm just going to double check that. 40 times 2 squared, which is going to be 4, equals divided by 12. Just got to be sure. So this is going to be 13.33 repeating kilograms meters squared of moment of inertia times alpha. So that we're going to flip it and multiply it by 60. So 60 divided by 13.33. So this is going to have 4.5 radians per second squared, and that's going to be alpha. Okay. And they want to know how many revolutions does it make to reach 200 rotations per minute. Okay. So what's your revolutions per minute? So the first thing we should probably do is convert this from radians to of revolutions per second squared, and then convert that to minutes. So we're going to divide this by 2 and divide it by pi equals, so this is going to work out to be 0.716 revolutions per second squared. Okay. Yeah, revolutions per second squared. Okay, and now let's turn this into minutes. Okay, so I'm just thinking about the problem, and I think it might be easier just to convert leave this as revolutions per second squared and convert this final omega, because they're giving you a final omega, and convert that to revolutions per second. Okay, so let's do that right now. Okay, so here's our alpha. Our omega final is going to be 200 revolutions per minute, and we're going to multiply that by 1 minute, and we're going to divide that by 60 seconds. So that's going to be 200 divided by 60. So what is 200 divided by 60? 200 divided by 60 is going to be equal to 3.33 revolutions per second. So this is 3.33 revolutions per second. So now we're basically just doing a rotational motion problem, okay? And they want to know how many rotations does it make. So they want to know how many theta in revolutions it makes before it reaches 3.33 revolutions per second starting from rest. Okay. So what I'm going to do is going to practice that procedure for motion. So I'm going to make a list of my variables. Omega final, delta t. And I think we want to know how long, which, not how many revolutions. I'm sorry about that. That should not be there. We want to know how much time it's going to take. So let me get rid of this. Let me get rid of this. We want to know how much time it's going to take to, starting from rest, to get to 3.33 revolutions per second, accelerating at 0.716 revolutions per second squared. So we actually want to know what time is. We want to know how long it's going to take in time. Omega initial, that's going to be 0 revolutions per second. Omega final, we just figured out and converted it to seconds. And then alpha is going to be 0.716 revolutions per second squared. Okay? The only variable that we do not have is theta revolutions. So essentially, we have to use this equation. This is the only equation that does not have theta in it, theta revolutions. Okay? We're going to solve this for time. Omega initial is 0. It's alpha times t. And then we're going to divide both sides by alpha to get the time. So we're going to go ahead and take omega final, which is 3.33 revolutions per second, and we're going to divide that by 0.716 revolutions per second squared. So let's go ahead and do that right now. 3.33 divided by 0.716. So about 4.65 seconds. So here's what we're going to get. 4.65 seconds. Okay. So I know from your book, the solution that your book has is a little bit different from mine. Well, how they did it, but I think I did an extra step. They converted omega to radians per second and just kept alpha in radians. But we basically got the same thing. So this concludes all of dynamics. Okay, so hopefully you learned quite a bit from this. Again, sum up the torques just like you do with statics. But now, since there is going to be an alpha, you'll have to sum the moments of inertia. You always sum them. They never subtract. And then multiply that by alpha and then solve for whatever they're asking you to solve for. Okay? Thank you. Okay. Have a good night.